The orientation to your suit?
I can see a bed.
Exactly, I can see myself better. What is happening, man?
Now I
Just
can
a
see your
minute.
face.
Can you see me?
Yeah, you I can see. Not you both though.
No, I'm not able to see anything out there.
No.
Is visible anything out there?
I was just asking if the filter out there is fit for use. I was just asking if the water filter out there is fit for use. Yeah, okay, don't use now, I get it, fine. I'm in the class. Yes, can you hear me? Sorry about that.
I can hear you, that's fine. No issue. I can hear you. What can you see, dear? Because I'm getting a blank.
So I just see some shades of grey, nothing meaningful.
I'm giving you a call again, that's fine.
So, no copy.
Yeah, I'm not able to get anything. Anyway, if you're able to see, so be it, I'll start. And if I'm going beyond the contours of what is getting captured, let me know on it. Okay, dear?
Yes, can you just flip orientation, please?
Yeah, sure.
Afternoon, Nishita. Long time no see.
Yeah, same here. Shita, she is never in a position to communicate with us. I don't know what is wrong with her device. Is it okay now, Vasudev? Shall we begin?
Yes, sir.
Okay. So to begin with, please write, and please let me know if I am beyond the threshold.
Yeah, sure.
What we have to write is, let me ask you, what is internal energy to either of you? Let me ask either of you rather, what is internal energy? How you define internal energy? How you define coordinates? So with the answer, and the simple answer is, internal energy of any system, be it any system, animate, inanimate, which system you are referring to, it can be discussed or defined in terms of few easily measurable properties. In terms of few easily measurable properties. Okay, dear?
Yes.
Properties which can be easily measured. Easily measurable properties. And these properties, is it visible what I'm writing there?
So it's a little bit too much to the right. If you can just shift your book a bit to the left, you'll be fine.
This way?
The other way.
Okay, fine.
To the left.
Okay. So this is what we have in terms of few easily measurable properties, and these properties are allocated, you may say an epithet, which is what is called thermodynamic coordinates. Thermodynamic coordinates. So what basically are thermodynamic coordinates? They are the parameters. You may say they are the parameters to measure something. Something which can be easily measurable is what is required to define internal energy of any system. Internal energy of any system can be defined in terms of easily measurable properties. They are called thermodynamic coordinates of the system. To cite an example, just to cite an example, let me get a coordinate system for medium gaseous. If I'm talking of gaseous system, then internal energy of gaseous system can be defined in terms of pressure, volume, temperature, and quantity. Pressure, volume, temperature, and quantity. So what are these to us? This is a set of thermodynamic coordinates. What we stand beneficiary of is this set will define internal energy of the gaseous system. I am to mark over here, I am referring to any gas. It's not ideal, but real. If it is ideal, then there will be a relation shared between these thermodynamic coordinates. By the way, any system you take, thermodynamic coordinates are experimentally found. For example, if I am to state my body as system, then to define internal energy of my body, I need to allocate with, of course, many an experimentation if possible for us. We'll get into, we'll indulge and come with an inference that what are the parameters governing internal energy of my body. And those parameters will be put under the heading thermodynamic coordinates of my body. Now, thermodynamics coordinates are not independent. It is not Cartesian coordinate that we are referring to. Cartesian coordinate, when I'm citing Cartesian coordinate, trying to get a Q or trying to establish a parallel, I would say it is in odds with. Why it is in odds with Cartesian coordinate frame? The simple, the basic reason there being Cartesian coordinates are not dependent on each other. Remember?
Yes, sir. Independent.
Cartesian coordinates are not dependent on each other, whereas the thermodynamic coordinates are dependent on each other. They depend on each other. And they depend on each other. That dependence can be represented in form of an equation. That dependence, if we get into delving deep, then that dependence can be represented in the form of an equation. The equation is what is called, can you tell me what is that equation called?
So the ideal gas equation.
What do we name that equation? Yes, carry on, Vasudev.
So the ideal gas equation?
Yes, it is called state function, right, dear?
Yeah, state function.
It is called state function. PV minus nRT is equal to 0. This is how we relate thermodynamic coordinates for particular system, and that system being, as said rightly so, Vasudev, ideal gaseous system. PV is equal to nRT follows only for ideal gaseous system, and this is what is called a state function. State function. So basically, what is state function? State function being a relation between thermodynamic coordinates, and what in turn being thermodynamic coordinate? Thermodynamic coordinates are those measurable properties which define internal energy of a system. If these coordinates, as I've cited example of gaseous system, ideal gaseous system, if these coordinates, let's say, remain same when I'm executing a process. If I'm into executing a process and these thermodynamic coordinates are unscathed, undeterred, then that state is called thermodynamic equilibrium. That means you will not have a pressure gradient, you will not have a volume gradient, temperature gradient, they will all be 0. If we are able to meet such a situation, happen to chance on such a situation, then we are to say our system is in what equilibrium? Thermodynamic equilibrium. Only then we will say thermodynamic equilibrium. On contrary, let's say there is only temperature which is not changing. Only temperature is not changing. So what we have to say? Certainly we will not be able to say the system is in thermodynamic equilibrium, but we are within our rights. We are to claim that that system will enjoy which equilibrium? That system will enjoy which equilibrium? Thermal equilibrium, right, yeah? That system will enjoy which equilibrium? Thermal equilibrium. If one of the coordinate is not changing, which over here, temperature is not changing, then we can say It is enjoying which equilibrium? Thermal equilibrium. If all are not to change, if you're not having any gradient, then we are to say it is enjoying what equilibrium? Thermodynamic equilibrium. So be very careful. Thermal equilibrium, thermodynamic equilibrium, constant pressure equilibrium, what are they? We'll be naming as we proceed, as descends the knowledge on us. For now, I'm stating first what is thermodynamic coordinate stated, then what is state function, and what that relation is called. The relation which establishes an equation, what is that equation called, and what to us is the state of thermodynamic equilibrium. It begins with a law, which is called Zeroth law. What is it? Pretty simple, pretty logical. Come on, you know this, isn't it? If A is in thermal, mind you, not thermodynamic. If A is in thermal equilibrium with B and B is with C, then A and C are in thermal equilibrium with each other, right? Yeah.
Yes, sir.
Am I clear?
Yes, sir. Sorry, I was muted.
Okay. If A is in thermal equilibrium with B, simple example, if I touch wall of classroom, if I'm touching this sheet, and I don't find any change in temperature of my palm, I don't find any change in temperature of sheet, then sheet and palm are in thermal equilibrium with each other. Now, this sheet is touching, let's say, one of the stand of table which I've kept it on. So that table, there's no change in temperature. Sheet, there's no change in temperature. When touching each other, then sheet is in thermal equilibrium with table stand. If I now touch my palm with table stand, then palm and table stand will also be in thermal equilibrium with each other. Pretty logical. A is in thermal equilibrium with B, B is in thermal equilibrium with C, then A and C are in thermal equilibrium with each other. This is called Zeroth law of thermodynamics. And that is because first was already defined, and it is an important, by the time we got to know on that we can have one more. First was defined, and we didn't try to tweak, we didn't try to change the order, keeping the order. This was given name Zeroth. Zeroth law of thermodynamics. Now, what is important to us is next is coming, which is first law of thermodynamics.
So before you proceed,
First
could you
law.
move your book to the
Yeah,
left?
Yeah.
So could you move your book to the left? It's a lot to
Why
the
not?
left, actually. I can see the left edge of your notebook, but I can't see what you're writing on the right.
Okay.
So, no, you're actually going the wrong way. The other way, all the way the other way. Yeah, even more. Yep, keep going. Yes, yeah, that seems fine.
Okay. Good enough?
Yes.
So this first law of what is first law of thermodynamics? We'll write next. First law of thermodynamics, please do write. Just a minute. Okay, stable now. First law of thermodynamics. What is it to state? Thermodynamics. I take a system, any system. I give some energy to this system. Q. Now I have transferred energy. Energy can be transferred in form of work. Energy can be transferred in form of heat. I wish to distinguish. Can you tell me what is one differential between heat and work? Yes, Ishita, I would like you to speak, Ishita. It's been quite some time we got to hear you. Come on. Set your vocal cord, dear, or do something about your device. Can you hear Ishita Vasudev?
That's negative.
Hey, Ishita, come on, dear, do something about your device. Are you able to see her? I'm not able to see either of you.
Listen, my video is actually off.
Oh, yours is off.
Yeah.
Ishita, yeah, good. That's good. Come on, Ishita, you discovered your voice eventually, your vocal cord. Yeah. Yes, please speak.
Right, right. I'm not able to see your screen. It's completely black.
I know, dear. There's something wrong with my screen. I'm also not able to see. That's the reason I seek your help. Can I see both of you at least? I'm not able to see myself. Yes, Ishita, will you do the favor?
Yes, sir. You want me to switch on the camera?
Yeah. And same with Vasudev. Yes,
Alright.
Vasudev, please.
Yes, I don't know if my net will sustain it though. I'm on like mobile data. I'll try that.
Okay, Ishita.
Yes, sir. Yeah.
Will do. Yes, Ishita, you can show yourself occasionally, right?
Yeah.
Huh? Okay.
Yes,
That's
sir.
good to see. You're visible as well as audible today. Both the bytes are working. Okay. Okay, look over here. I think I'm not able to see myself. Please help me here. I'm completely black. I can share the screen with you after the class, what I'm able to see. I don't know what has happened to my side. We'll have to do something about it. So this Q is what being transferred to the system.
Wrong camera placement.
Q is what being transferred to the system. Is it okay? Visible?
So the scaffolding you're using to hold the camera in place is blocking it.
Okay, now.
Okay, yeah, that'll work. No, that won't.
Change will. It's simply black screen.
Yes, so that's fine. That's perfect. Don't move it. Perfect.
Okay, fine. So Q is generally a notation for heat. And you're aware of, need not ask or need not more indulge on time. Q is heat, and heat means transfer of energy in which two bodies at differential temperature are involved. Means when energy flows owing to difference in temperature of bodies, then that energy is termed heat. For instance, I want to heat water kept in a cauldron. So I can place it on flame or can with vehemence shake it. I want a differential temperature of a meager or minimal. So I can with vehemence shake it or I can simply place it over flame. In second case, when I'm placing over flame, temperature rise is owing to differential in temperature of water and flame. If they are at same temperature, there will be no rise in temperature of water. In second case, there is no difference in temperature involved. You can immune outside system which is shaking it vigorously by using insulator. Yet temperature will rise. So when there is involvement of temperature difference in flow of energy, that is termed heat, else work. Heat is generally abbreviated by symbol capital Q or H. So what I do over here, I transfer energy to system. I find therein change. I find therein a change. Therein a change. Change in what? Change in internal energy of the system. And find the system doing work W on the surrounding. Please be very careful of the equation which I'll write next, because it is in odds with what you have studied in chemistry. And why so I'll get to know. And that is their brainchild, what they do, their figment of imagination. I am not to protest it. I'm just writing what we do follow, we physicists. So I am a pendactic stickler for physics, so I'll go by it. What do we write is energy equation. Q is what I have coded to the system, delta U being used by system, and so is W. So Q, what I did accord to system, some part of it did go in raising internal energy or changing internal energy, and the other being used by system to do work on the surrounding. Mind you, used by system to do work on the surrounding. This is an equation which has got nothing to do with state. It is true for any state. So till now, we are good. We are ambivalent and we are accommodative. Q provided, delta U use, and W is the work done by system on the surrounding. I want to use this term. I want to use this term for gaseous system. In that case, what we can do is pretty simple. Q I keep as it is, delta U is delta U, and for W we can write P delta V. P delta V. What is P delta V over here? Work done by gaseous system. For that, what I am to do, I am to tell you, take a piston, the volume is V, assume that the piston moves slightly by dV so that the pressure is maintained. Mind you, so that the pressure is maintained. Then work done will be what to us? Work done will be P into dV. And why so is pretty obvious. Work done in general is F into dx, and F is P into A. So P into A dx, A being the area, we get it as P dV. When we have work, we will be marking P dV. For total work, we will be marking P dV integration. So dq, the differential form of it will be dq. Am I within the contours of camera?
So now you need to take it down.
Okay. So dq is equal to du plus pdv, the differential form. dq is equal to du plus pdv. Heat which is being provided, energy which is being provided in form of heat flow is to increase internal energy and being utilized by system to do work on the surrounding, on the ambience. This is what this equation is indicative of. In chemistry, you have minus pdv. Why? Because there we take work done on the system. This is work done by the system, work done on the system. This has costed dearly to a student who could have gotten the bracket of 5 in year 2019 with Akash. Instead of plus, there he used minus and lost the marks, thereby opportunity, and the rank fell to 200 plus. Else it would have been single digit. Please be mindful of it. dq is equal to du plus pdv. Pdv is the work done on the surrounding by the gaseous system. Before I proceed, few mechanical definitions. And what are they? What is dq by dt?
Just a quick clarification here. Isn't this equation valid for
Yeah.
both chemistry and physics? We get minus W in chemistry because we take work to be minus PdV, right?
Yeah, right, of course. How can we be odds with the equation here?
Yeah.
It's about interpretation.
Yes.
Yeah, we take minus because there we take work done on the gaseous system. Okay.
Yeah.
Here I'm taking work done by the gaseous system. Getting it?
Yes, sir.
Okay. Now, few definition. dq by dt. What is dq by dt? dq, of course, is heat, and dt, the rise in temperature. So, what do we call this? Heat capacity, right? Yeah. Amount of energy. Please write down. Amount of energy required in the form of heat flow. Please make it categoric. Make that distinction, class. Amount of heat required in the form of heat flow to raise temperature of a substance, by unity. That unity can be degree centigrade, degree Fahrenheit, or Kelvin. Is called heat capacity. I'm using a symbol C for it. Then we have dq by dt by m. M is mass over here. Amount, what is this? Similar to the previous, but mass being factored in. So what do I say? Amount of energy required to raise temperature of unit mass of a substance by unity. Unit mass of a substance by unity. What is this called? Specific heat capacity. Yet another molar heat capacity, you know what to write for that. dq by n dt, and there you will mark amount of energy in the form of heat flow required to raise temperature of unit mole of a substance by unity. So that is another definition which we will be making good of. For now, please answer which of the two is independent of mass.
So,
which of the two is
specific heat
mass? Specific heat capacity is independent of mass. It doesn't depend on mass. And you know the reason for it, because this is about per unit mass. So this is independent. What next I'm to do is to work on this equation, but we'll work on this equation under a rider, and that rider being, I have taken a system, internal energy of which depends on temperature and volume. Is it okay?
Yes, sir.
I have taken a system, let's say I have taken real gas. Find here. Internal energy of a system is dependent on which two parameter? Temperature and volume. Am I clear, Shruta?
Basically, we need to choose 3 or 2 out of 3, right?
Yes.
Yes, dear. Yes, Vasudev.
We just need to choose 2 out of the 3 available to us.
Yeah. 2, 3, 4. And you can choose. I'm taking 2. It'll be easier for me to explain it to you what exactly I'm looking forward for. So what will be du Vasudev over here? Du mathematically? What do you say? Partial derivative of with respect to temperature, correct?
So you need to shift
At
it
constant volume. Not visible?
Nope.
Over here. Visible?
Yeah. Yes.
Temperature, volume. And I want to differentiate it. So partial derivative. What do we write? Differentiation of u with respect to temperature at constant volume into dt. This is one function. And then again, now this you will not be getting there anywhere. So please be very careful in understanding what I'm trying to suggest over here. Differential of u with respect to next volume at constant temperature
So
into dV.
lighting does leave much to be desired.
Yeah. Just a minute.
Yeah, that's fine.
So this is what we have. This is for du. Just placing in our equation. If we place in our equation, dq is what to us? Is du. So du is this to us. du dt at constant volume into dt plus partial derivative of u with respect to volume at constant temperature into dV, and what we had edV. I write it over here. The other factor, this is dq to us, right?
So what is the first equation you've written? U times TV. What is that? The first
U
one.
times, so there's a U is function of temperature and volume.
Oh, okay.
And then I'm trying to find what will be du for it.
Yes,
So
okay,
du
got it,
will
got
be
it.
partial derivative of u with respect to temperature at constant volume into dt plus partial derivative of u with respect to volume at constant temperature into dV, right?
Yes, sir.
Mathematically. Okay. Now this being the case, what next? I take dt down, what we get is dq by dt is equal to partial derivative of u with respect to constant temperature, volume plus du dv constant temperature plus p whole into dv by dt. Do you check there? Okay.
Yes, sir.
Okay. Now we can read this equation under the lens of constant volume. Let's say I want to read this equation under the lens of constant volume. That means I want to read from this equation, this is the parent equation, let me mark A. I want to read dq by dt at constant volume. What do I end up getting? Is du by dt at constant volume. Why? Because this term will be 0, right? Getting it?
Yes, sir.
Now, dq by dt at constant volume means heat capacity at constant volume, correct?
Yes, sir.
What you get to see from here is du by dt at constant volume is equal to heat capacity at constant volume. An important equation, I'll get back to it later. Very important equation. Cv is equal to partial derivative of u with respect to temperature at constant volume. I'll get back to it later. For now, I'm to use this in equation A or before of it. So what I do from here, dq as it is. Then we had this. I think I'm within the threshold, correct?
Yes, sir.
Okay. Instead of this one, I'm now placing CV. So CV dt plus just du instead of du CV dt plus as
so
it
now
is
you're not.
du dv.
You need to move the book.
Okay. Okay. Good now?
More.
Okay. More.
Yes, sir.
Is it okay? Fine. Good now?
Yes, I can, but I won't be able to see the next line you write. It's like at the very bottom of the screen. Yeah, yes, that's fine.
So plus P whole into dV. Okay. This is what we get. Just a substitution, CV. I'm writing CV over here. Nothing much. Now, we are to read this is equal to CV plus this factor du dV at constant temperature plus P whole into dV by dt. Let us read now this at constant pressure. When I do this, I get over here at constant, this equation AB, let's say C. Equation C now I want to study for constant pressure. So I'm applying constant pressure everywhere on equation C. What do I end up getting in this is Cp is equal to what to us? Cv as it is. Cv will not change. Constant pressure or constant whatever it may be. Cv is a constant to us. Plus, what we have to see over here is du by dv at constant temperature plus p dv by dt at constant, what is it? Pressure I have taken at constant. This read will also be at constant pressure. This read, entire of it.
Yes, sir.
Will also be at constant pressure. Okay. So this we got. Now I won't be able to further. Why? Because I want to get rid of this term. If I want to get rid of this term, what I have to ensure? I'll have to ensure that internal energy is free of volume. If I ensure the internal energy is free of volume, I'll be able to further with this equation, else I'll keep it to this form. This is the parent form to us.
So
I'll keep it to this form for a system. Yeah.
Can't you make this argument? The internal energy is dependent on any two of the thermodynamic coordinates parameters of a gas, right?
Correct.
So right now we're saying temperature is constant. That was the condition on the derivative itself. But now we're also saying pressure is constant. Since two of these parameters are constant, we can say that the internal energy won't change.
Yeah, I would say that I am over here trying to figure a system of which internal energy is dependent only on temperature, dear. So I'm trying to make it in the proximity of ideal gas scenario. You may be aware of. I'm not saying that internal energy is constant. What I'm trying to suggest is internal energy can depend on three parameters for real gas. And they being temperature, volume. If I've taken a certain amount of a real gas, then internal energy will depend on temperature, pressure, volume, right?
Yes.
Certain amount taken, amount fixed. Temperature, pressure, volume. And then what I did say, that let's keep pressure aside. Why? Because I don't want to carry that along. So let's keep pressure aside. It depends only on temperature, volume. I did establish a relation. Now what I'm saying is, internal energy is function only of temperature. If you are hell-bent on taking no, I don't want to go with internal energy dependent only on temperature. I want to go with internal energy dependent on temperature, volume, pressure, ball. So be it. In fact, there's a question also in SC Mama, which asks for, tell me for real gas, Cp minus Cv is equal to what? So you'll get to know about it. There'll be one more term. That's it. If you want to keep pressure as well, there'll be one more term. What will that be? du dv at constant pressure. Correct, dear?
Yes, sir.
There'll be one more term. What from here I want to jump to is from real gas. Real gas whose internal energy was dependent on or were dependent on temperature and volume. From that real gas, I'm transcending to a system in which internal energy is governed by only temperature. A system of which internal energy is governed. System of which internal energy is governed only by.
So
Am I audible?
Yes, sir. But if you say that, then at constant temperature, the derivative of u with respect to anything should be zero,
Hello?
right?
Hello?
Yes, sir. Can you hear me?
Yeah, I will be joining in 15 minutes. Yeah, I'm on way. 10 to 15 minutes. Actually, I'm in the class. 10 minutes.
So was that directed to us? Hello.
Yeah. Just a minute. Better now? Can you hear me now?
Yes, sir, I can. But your screen is flipped.
Screen is flipped. Now?
Yes, sir. So as I was saying, if you propose that internal energy should be only a function of temperature, then shouldn't the partial derivative of u with keeping temperature constant, shouldn't that be zero?
This will be, of course.
Yeah, that'll be zero.
This will,
Yes.
okay? This will be zero. Maybe that only. This is proposed for internal energy being function of temperature and volume both. So you may argue over here that this is for a real gas in which temperature and volume are to govern internal energy. Now I am transcending to a system, internal energy being governed only by temperature. Thereby, what I am trying to suggest is I am from real gas moving to ideal, because for an ideal gas, internal energy is governed only by temperature. You must be aware of it, correct?
Yes, sir.
What are the two terms which go in defining an ideal gas? First is internal energy is governed only by temperature, and the second, it is in adherence to state function PV minus nRT is equal to 0, correct?
Yes, sir.
Using it over here, what can we say? Cp is equal to Cv plus, this is gone because there is no more to be seen, P dV by dt, right here? This equation holds good for an ideal gas. Agreed or not?
So, yes, but your writing is out of bounds again.
Is it okay?
Yes, sir.
Now P, what can we write for P? P is equal to nRT by V, right? Right? Or V is equal to nRT by P. I want to make V the subject. So V is equal to nRT by P. dV by dt, then what to us? It is nR by P, correct?
Yes, sir.
Okay, visible? Visible?
So, but that is assuming we're keeping pressure constant, right?
Yeah, we are. Keeping pressure.
Okay.
Because there's a relation between CV. I'm going to keep pressure constant. In fact, I'm keeping pressure over here constant only, then we have P out of the differentiation symbol. Correct?
Yes, sir.
So Cp is equal to Cv plus P nR by P. T and P gone. Figure it as Cp is equal to Cv plus nR. This is a Mayer's equation which we get Cp minus Cv is equal to nR. Please be careful, mindful of what is Cp over here, what is Cv over here. If you divide by n, that will become molar heat capacity at constant pressure and molar heat capacity at constant volume. In that case, we write Cp minus Cv is equal to R. But here they are heat capacities. Here if you keep n, then heat capacity divided by n, then molar heat capacity, correct?
Yes, sir.
Okay. So, as Siva has asked that in real case, a real gaseous system, what will be Cp minus Cv? I think you'll be in a position to answer now. Cp minus Cv will be equal to R, greater than R, less than R. What will you say? Cp minus Cv for a real gas, what will it be? Less than R, equal to R, greater than R? What is your take? Tell me, Vasudev.
Could you just move a little bit up so I can see that equation?
It was a term which we have just counted on, which one thing this, we dispensed it.
So it'll be
If it is
CV
real,
minus CV will be greater than R, right? Yeah.
Greater than R, right? It'll be greater than R. Getting it?
Yeah, but that is assuming du by dv at constant t is positive.
That is assuming what is positive?
Du by dv.
The gaseous system will be positive. It is to be positive. Internal energy will increase with volume, right?
What?
It will least for solid. It will least for solid. Internal energy will be an increment, a function which is increasing with volume. So it ought to be positive in general.
This is because intermolecular attractions are lesser, so less binding energy.
Yeah. If at all it's to be negative, that can be a case possible with solid.
Yes.
So that is what we get over here. Now getting back to the equation which I said I'll be after of the dispensation and culmination of what we were into, will return. I'm returning to this. CV is equal to this. Now apply this to an ideal gas. This again is to get us a very important relation. Shall I keep it this way so that it's visible? Is it visible? The free end, this side?
Yes, sir.
Okay. If I'm applying this equation to an ideal gas, CV is equal to what to us? Then I will not write partial. Then I will write du by dt, right here. Ideal gas, where that is the only factor it depend on. Correct?
Yes, sir.
So partial will change to a complete. Partial is no more. It's a complete differentiation. What do we get to see then from here? Du is equal to CV dt. A very important relation. Du is equal to CV dt. Delta U is equal to CV delta T. Okay?
Yes, sir.
Okay. So we saw for a few equations out here. Please be mindful of what all we have got from here. We got CP minus CV is what to share with R. We got what is du to share with CV. And we got what it is for real and what for ideal. Of course, we'll be sticking to ideal gas system. Henceforth, we'll be taking only ideal scenario into account. Du is this to us. What next we are to do is to check. What next we are to do is to check the number that we do have against C. How many C? What is the number? What is heat capacity dependent on? How many heat capacity can we get for a system? One we know CV, the other we got to know CP. So how many heat capacities according to you we may get? What is the number of heat capacity we can get? Yes, Ishita, can you take? I am known to CP, I am known to CB. Do we have any other?
So CT definitely is nonsensical. I don't see anything else.
It's nonsensical. It doesn't sound sense to us. Divorce of idea. Any other that you can facilitate, dear? How many can we have? How many heat capacity can we get to see? Can we have? What do you say about it? So we can have as many as infinite, right? Yeah. We can have as many as infinite. Why? Why do I say so? Why do I say that we can have infinite? Now, we had an equation Q is equal to delta U plus W. Now, delta U, what does delta U depend on? U depends on thermodynamic coordinate of system. It doesn't depend on process. Whereas Q and W, they depend on process. U depends on state. I'm moving from this point to this point. I can move following this path. I can move following this path. Delta U will remain. I follow whichever path. So what is delta U? Delta U is state function. State got changed from where to where? It doesn't depend on path. Whereas Q, it depends on path. W, it depends on path. Both Q and W will depend on path. Delta U is state function, doesn't depend on path. Delta U depends on thermodynamic coordinate of system. So that being said, how many C we can get? We can get infinite C because C depends on process. If it's volume constant, then constant volume, pressure constant, constant pressure, temperature constant, constant temperature. There can be process which is amalgamation of three. There can be process which we cannot bracket in volume constant, pressure constant, or temperature constant, but there is something which do they have in common. In that case, what we are to suggest is what is the commonality which relate CP, CV, and C. And to get to it first, how many C we can have? C can be infinite. C depends on what is apparent from here. C depends on process. It depends on process. If I take a polytropic process, by polytropic what I mean, if I take a process CV raised to power X is equal to constant. It entails all the process, by the way. CV raised to power X is constant. How does it entail all the process? If X is gamma, then we get PV gamma is equal to constant, correct?
Yes, sir.
If X is 1, then we get PV is equal to constant, correct?
Yes, sir.
Similarly, if X is 0, then we get pressure is equal to constant, right?
Yes, sir.
So it entails all the process. Can you tell me when will I get volume constant? For X what I'll get volume constant? Because we saw for temperature constant, PV is equal to constant means temperature constant, that we get at X is equal to 1.
So X is equal to infinity? I don't know.
X is equal to infinity, absolutely we'll see volume constant. You can take one V over here and bring the other V down, and that will get you volume constant. Okay?
Yes, sir.
That what we can do is PV is to power X, we can say PV is to power X, we can take 1 by X and accordingly work it out, right?
Yes, sir.
So that will get us volume constant. Okay. In that case, this is a process which envelopes all the processes known to us. So I'm taking this as the process and trying to fit in the relation which we got. Which relation I'm hinting at? I'm hinting at the relation dq. dq is equal to du. I'm hinting at this relation. Is it within the boundaries? dq is equal to du
No.
plus pdv? No. Okay. Now?
So now we can see what you've been writing since the last 2 minutes.
Okay. You want me to hold it now?
So could you move it a bit more down? Yeah, that'll do.
Okay. So this here, dq by dt now is equal to du by dt plus p dv by dt, right? Yeah. Now dq by du by dt is what to us? We have already established is CV for us. And then pressure, I'm referring to PV, X is equal to constant. So you know what we'll get over here. Could you please help me on that? PV X is equal to constant is what I have taken, and I want P dV by dt to be substituted. So what should I write?
So you can just write P is equal to constant by v to the power x. And then you can cancel all the dt's
Okay.
and integrate.
Okay, so what will be dV by dt? Can we substitute dV by dt here?
So dv by dt?
P dV by dt. I want a substitution over here. What can it be? dV by dt. I have taken which process? I have taken PV X is equal to constant, right?
Yes, sir.
I have taken PV X is equal to constant. Okay. Pressure, if you want to keep, you can write it as K divided by V raised to power X. That is what you want, right here?
Yes, sir.
Okay. And in the previous case, when I took PV is equal to constant, I asked you to substitute for dV by dt, right? We took PV is equal to nRT. Do you remember?
Yes, sir. Yes. Okay, got it.
And that is true for any ideal gas, correct? Here, following the same, what we can replace P by is nRT by V, right?
Yeah, sure.
Because it's again an ideal gas, right? I'm not in any way taking a digress from ideal gas. I'm using it on an ideal gas, right here.
Yes, sir.
Process is this, of course. Process is PV X is equal to constant. But I'm not taking any departure from the ideal state of gas. Is it okay? So I'm still in my capacity to use PV is equal to nRT. Agreement or not?
Yes, sir.
Okay. So if I use PV is equal to nRT, then what do we replace this for? Tell me. What can this be replaced for? PV is equal to nRT being used. Instead of P, we can replace nRT by V, correct?
Yes, sir. Then you can integrate. Yeah, sure.
So what do we get over here? If I may ask, can you get me a replacement for P dV by dt? That is what I'm looking forward for. In the previous case, we got the replacement as NR, correct? In the previous case, we got the replacement as NR. Previous means which case? When I took pressure to be constant, correct?
Yes, sir.
But in this case, pressure is not constant. When you took pressure to be constant, we got P dV by dt, P we took out, and accordingly we got a relation. Now I cannot take P anymore out because P is not constant to us. So what do we say? P is equal to what to us? P is equal to K by Vx, right? So K by Vx into dV by dt is what being suggested, correct?
Yes, sir.
Okay. Now, what other than that? What do you suggest? What will be this P dV by dt shaping to? This is what I'm looking forward for. Can you get me know on what will this shape to for the process which I have indicated? And the process is polytropic. I have taken the process polytropic. dV by dt. What will be dV by dt? What will it boil down to? Any one of you? Yes, dear.
So just 1 second. Let me work the math.
Okay, fine. Let me ask a broader question to you. PdV, this is PdV, right? This is dW, work done, correct? Work done. This is work done, correct?
Yes.
This part is work done. If I write it as dW, then this is work done, correct?
Yes, sir.
Correct? And PdV integration, if I take total work I get, right? P can be substituted as, from here, what we can write for P? A by Vx, correct?
Yes.
Into dV as it is. Agreement here?
Yes, sir.
So what do we get this as? K v raised to power minus x plus 1 divided by minus x plus 1, correct?
Yeah.
Is it fine?
Yes, sir.
Okay. So P dV is what to us? Is this to us? K v raised to power minus x plus 1 divided by minus x plus 1. Correct?
Yes.
Shall I write it up?
So
Shall I
you
take
can
it up a
just
little? Flip the page?
Yes. No, don't flip the page. Just move the book a bit. Yeah, towards the.
Okay.
Just push the book up.
First, I'll write first over here. K v raised to the power minus x plus 1
So I can't see
divided
that.
by minus x plus 1. Okay. Now?
Yes, that I can see.
Okay. This is dq by dt. dq by dt, this factor, and by the way, this is pdv, so be very careful. I'm using this equation. I'm highlighting the equation which I'm going to use is dq is equal to dt plus pdv. This is pdv. This is pdv.
So shouldn't
let me
then
write
du
it.
be cv dt? Yeah. And dq. Yeah. Right. Sure.
Yeah. Okay.
Yes, sir.
Okay. Now, I'll have to shift it there. Shall I?
So 1 second. Yes, sir.
Okay. I'm shifting it now up. Check the area visible blank so that I can write. Visible?
Yes, sir.
Blank area? Okay. So dq, I rewrite my equation. dq is equal to du plus pdv we got. And pdv for a polytropic process, what we got to see is We wrote for polytropic, PV is equal to, so K divided by Vx I wrote over here. dV, integrated it, we got it as K V raised to power minus x plus 1 divided by minus x plus 1. And if I go for integration, accordingly, we'll place it later. But for now, K V raised to the power minus x plus 1 final and minus K V raised to power initial divided by minus x plus 1 is what we are getting. Now this K can be written as P final, V final, that is what we have taken. P final, V final, we took it as P final, V final raised to the power X. And we can take as initial as well. Why? Because we are into polytropic process. Second one, P initial, V initial X, that is for K I'm substituting, and V initial minus X plus 1 whole divided by minus x plus. Why did I do so? Pretty simple. You know why I'm doing this. TF and this becomes VF, right?
Yes, sir.
Then this one, EI, VI, and minus x plus 1. Okay, yeah?
Yes, sir.
Okay, now this can be marked as NR dt, right?
Yeah.
And minus x plus 1. Right? Shall I move down?
So one second. Whatever we've got plus
Yeah.
NCV dt is equal to dq.
Yeah.
Okay.
This I rewrite over here. dq is equal to what was du, and we got p dv as nr dt divided by minus x plus 1, right?
Yes, sir.
Okay. Now dt, as we wanted dt not to be seen, we will write first dq is equal to what was du was cv dt, so c dv dt plus nr dt divided by minus x plus 1, right?
Okay, out of bounds again.
Yeah. Check, right?
Yes.
Now dividing dq by dt is equal to cv plus nr minus x plus 1, right?
Yes, sir.
What do we get to see from here then? This is nothing but c. So c is equal to cv plus nr minus x plus 1. Do check here. Is it? Just check once, please.
Yes, sir. One second.
Delta t. We can also write it down as c is equal to cv plus nr and t initial minus t final. Then you'll get x minus 1, right?
Yes, sir. So, you need
Mind
to
you, that is not delta t
move the
anymore.
book again.
This is not delta t anymore. This is t initial minus t final, okay?
So, can't
Sir,
see
can you
what
drag
you're
down the screen?
Yeah. This is t initial minus t final. Getting it there?
So, you still can't see it. You need to move it more down. Or up from your perspective. Yeah.
Getting it? This got in this relation? So what is this indicative of? It implies we can have as many value of C as process, correct?
So, one second. Where did you get TI
Process
minus
different-
TF from? They just seems to have popped up from
T
nowhere.
initial T final. Which one? Which one?
So, it wasn't there in the previous equation and now it's just there. Where did you get that from?
No. Wasn't there dq by dt nr delta t? This is not this equation. I'm writing delta t over here. This see dq by dt we wrote it there and then we took it down, right?
Yes.
And now 1 minus x, this will not be there, but I just want to tell you that dt that I'm using over here, they'll see in the denominator minus x plus 1, because this dt is change. If we continue with this equation and take it as minus of dt, then in denominator will be x minus 1. Because x will be greater than 1, so I want to take it as x minus 1. In that case, if I mark it as x minus 1, then this dt will not be dt, will be minus dt. And minus dt means what to us? Minus dt means t initial minus t final. That is what I wanted to indicate. Okay, dear?
So,
For now, the equation remains, which is this will be minus x plus 1. Otherwise, you'll have to place a minus over here, right?
yes, sir.
Getting it? Is it okay?
Yeah, it's okay.
Do check. And this is indicative of, we will have as many value of c as process, because process depends on x. What is the process depend on? X. If you take x is equal to 1, which process we are in? Constant temperature,
Yes,
right?
isothermal.
If I take x is equal to 1, what do I get this factor as? 0, I'll get c is equal to cv, correct?
So you won't get 0, you'll
Which
get division by 0.
Yeah, correct. Now, I'm coming to what will be CV. What will be CV, dear? How do we get CV? Because I want to check CV as well. What is CV? CP by CV. We wrote an equation, CP minus CV is equal to R. I'm coming to that now, dividing it by CV throughout. CV. This term is what is referred to as gamma. Gamma minus 1 is equal to R by CV. Another relation, very important, directly question are being asked, not in IIT of course, but in NEET examination. Gamma minus 1 is equal to R by CB, or CB is equal to R by gamma minus 1.
So you need
CV is equal to R by gamma minus 1.
move the book again.
Is it okay?
So we can't see it.
Okay.
Drag it down.
Way more down.
Is it okay?
No, you need to still go down.
Any good?
So you went the wrong way. You had to move the book up.
What should I do? Down?
Yeah, that way. Whatever you're doing, keep going.
Okay.
Keep
More?
going, even more.
Okay.
So that doesn't cut it.
Now?
Why don't you just push it all the way? Why are you doing it in like these small increments? And no.
What? Okay. This one? No?
We still can't see the last equation.
Wait a minute. And now it's visible? No?
Yeah, if you just move the book, push it, the book a little bit up, it'll be fine.
Now?
So we are not seeing the relevant part of the page right now.
I'm not able to see what I'm showing you here. What do I do today? Yes, Vasudev. Any good? No luck.
This is definitely better. We can see a lot more, but you're still not showing us the right page.
Nothing?
So you need to take the camera down. Other way. More. Go on. Keep going. Right, to the bottom of the page. Yes, sir. Gotta keep going. Right, more. I'll tell you when to stop. Keep going till I tell you to stop. Yes, stop. Right there. So just hold it for a minute. It's out of focus.
Sure.
So it's not resolving. It's where the focus can't make out anything.
Then let be this. Fine, we'll call it a day then, Vasudev. Okay? It's getting heated as well. Okay?
Yes, sir. How,
Take
how
from
about-
where we are have a hair culminating. I'll take from there, no issues. Okay?
how about you use a graphic tablet or something? I mean, we won't have to deal with this.
Come again?
So how about you use a graphic tablet or something along the likes? And we don't have to deal with you holding.
I'll be there. I'll be using the one that you are using, right?
Yeah, that one, something like that.
What? Maze, right?
Sir?
You're using Maze, right?
So what did you say?
Which one are you going to use it?
I'm using a Wacom tablet.
Okay. But no, Samsung I'll be able to. I'll be using tablet next time. Next class onwards, I'm to use tablet.
Yes, sir.
Okay. Thank you, dear. Thank you, Shila. Thank you, Vasu.
Thank you, sir.